So today we're going to be talking about more natural log derivatives. The title of today's lesson is actually not fully accurate because in all honesty, the very beginning of this lesson is going to be more just a review of everything that we've done so far, but we are going to get back into natural log derivatives a little later in the lesson, but let's get started. So today's plan, we're going to use today as another catch-up day to ensure we're understanding concepts before moving on. We're going to start with a drill of a bunch of questions that I want you to try either independently or in pairs. So you can work either on your own or you can work with a partner. It'll be kind of like we'll pause the video and you try it and then we'll go over it kind of thing. And then we'll review the natural logarithm from last class and do a few drill questions on that as well. And then you'll have your normal practice time as usual. Anyway, let's get rolling. First things first, this is one of those questions I want you to work on either on your own or with a partner, whatever you're more comfortable with. I just want you to find the derivative of f of x equals negative 3x to the power of 4 times cosine x. I'll just give you a little bit of a warning. There's not too much we can do to clean this up, but you'll want to pause the video here and give it a try. All right, I'm going to go over it now. So first things first, hopefully what you identify is that this is a product rule question because we have one piece times another piece. So especially when you see like some sort of a trig part to this, whether it's sine, cos, or tan, if it's ever multiplying something else, you can be pretty much guaranteed you're going to be using product rule, right? So anyway, first things first, the derivative of f is going to be the derivative of the first thing. So the derivative of negative 3x to the power of 4, which would be negative 12x to the power of 3, times the original second thing, so times cosine x, plus the original first thing, so negative 3x to the power of 4, times by the derivative of the second piece. Well, the derivative of cosine is actually negative sine x. So when I mentioned a second ago that there's not really too much simplifying you can do here, really the only thing I think we could do is take care of this double negative stuff going on here. So I would actually rewrite this as f prime x equals negative 12x to the power of 3 times cosine x. And then because it's plus negative negative, that just becomes plus positive 3x to the power of 4 sine x. So that right there, I would say, would be the simplest form of that derivative. Anyway, let's give the next one a try. Find the derivative of f of x equals cosine 4x squared times sine 5x. This one's a little bit trickier for sure. I will tell you also before we start this one, this is not going to clean up at all. So it'll be a one-line answer kind of thing. Anyway, pause the video here, give this one a try. All right, I'm going to go over this one now. So the derivative of this is actually going to be, once again, a product rule question because we have something times something else. However, there's another step that's going on here. When we take the derivative of this cosine 4x squared, because there's a whole bunch of stuff going on inside here, this would be considered a chain rule piece. The reason this is considered a chain rule piece is because this isn't just a straight up x in here. We got 4x to the power 2, so there's a lot going on inside there. And technically, actually, this 5x also would be another chain rule piece. It will do something important, so I shouldn't say it's like, oh, technically also another chain rule piece. It is another chain rule piece. It's just not going to be nearly as exciting as that 4x squared. Anyway, so if we're going to take the derivative of this, the overarching thing going on here is product rule. So we'll take the derivative of the first thing. Well, the derivative of cosine 4x squared is going to be using the chain rule, of course. So the derivative of the outside of that would be negative sine 4x squared. But then we have to multiply by the derivative of the inside. Well, the derivative of the inside of this function, so the derivative of 4x squared would be just 8x. So we're going to times this now by the original second piece, so sine 5x. And then we're going to add the first thing, which is cosine 4x squared. Maybe I'll even put that in brackets, times by the derivative of the second piece. So once again, this second piece here, sine 5x, that's going to be a chain rule piece. So let's take the derivative of the outside of that thing first. The derivative of sine 5x would be cos 5x. But then we have to times by the derivative of the inside of that. Well, the derivative of 5x would be 5. So that looks like an absolute nightmare. But if you actually look at how we can, like, try to clean this up, there isn't really much we can do, right? Like, this 8x isn't going to go in here or anything, and these signs aren't going to combine. So there really isn't anything we can do on this one beyond what we've already done. So this is where we just get to box our answer and say, yep, we're done. We don't have to worry about anything more. All right, next one. Once again, another question I want you to try either on your own or with a partner. Find the derivative with respect to x of that statement right there. Pause the video here. Give this one a try. All right, so for this one, this is an implicit differentiation question. The reason I know it's implicit is because there's y's built into the equation. So when we do implicit differentiation, we just take the derivative of each piece separately. So I'm going to start by taking the derivative of 7x3. That's just going to be 21x squared. That one wasn't too big of a surprise if you know your power rule. As for this next thing, 5y3, because we're taking the derivative with respect to x, we have to assume that y is a function of x. So this becomes like a really weird chain rule kind of piece. So what we would do first is we bring this 3 down like we do the normal product rule, or sorry, normal power rule on that. So that would be minus 15y squared. But then we have to also multiply by the derivative of the inside of the function. So in other words, the derivative of y. Well, the derivative of y with respect to x is just y prime. So as weird as that is, that would be 15y squared times y prime. This is going to equal the derivative of tan y. Well, once again, because y is a function of x, like we have to assume that, this is also technically a chain rule piece, but let's start by taking just the derivative of tan. If you don't remember what the derivative of tan is, and I don't blame you, it is on your formula sheet. The derivative of tan is secant squared of whatever was inside of it. So secant squared of y. However, like I said a second ago, this is also still a chain rule question. So I also have to times this secant squared y by y prime. That's the derivative of y. I'm actually going to clean that prime up. It looked like a 1. Make it a little bit more clear. There we go. That's a little better, right? So anyway, now we have the derivative of this. What we always try to do when we have an implicit differentiation question is we try to get y prime by itself. We got a y prime over here on this side of the equation, and we got y prime over here on the right side of the equation. Let's bring everything all onto one side. So I'm going to add 15y squared y prime to the other side. This gives me 21x squared equals secant squared y times y prime plus 15y squared y prime. Now that we have all our y primes on one side, I can factor them out. So this becomes 21x squared equals y prime times all the leftovers. That would be just secant squared y plus 15y squared. Last thing up here, because we want to get y prime completely by itself, let's just divide by this stuff in brackets here. I'll even like rearrange this around because I always like having y prime on the left. So I'll say y prime equals 21x squared, all divided by secant squared y plus 15y squared. And that right there would be your derivative. Not a very nice looking derivative, but at very least it did simplify a little bit. Like it wasn't like those other ones where it stayed just the same on both, but it is what it is. All right, next one. This one is much, much trickier. It's going to take quite a bit of writing on this one. I know in your booklet you don't really have a lot of room for it. That's my way of saying kind of write small. Find the second derivative for this function right here. My advice for you before you even get started is do the first derivative kind of on the left side of your page, and then do the second derivative on the right side of your page. That way you'll probably be less likely to run out of room. Another piece of advice here is clean up your first derivative as much as possible before you take the second derivative. That'll also help quite a bit. Anyway, pause the video here, give this one a try either on your own or with a partner. All right, I'm going to go over this one. This one's kind of interesting because quite clearly, since it's a fraction, this is going to be a quotient rule question. The other thing that's going on down in the denominator, it's like x plus 3 to the power of 3. That's kind of like a chain rule piece in there. You'll see when I go through this, it's not the most interesting chain rule piece. Like actually, it won't be really all that interesting, but it is still technically a chain rule piece. You'll see what I mean in a moment. Anyway, because quotient rule is kind of the overarching thing here, let's start with that. One other thing before I get going, though, this negative sign on the outside, I always just imagine it's up on top. That might make my life a little bit easier on this. All right, so anyway, quotient rule says, I'll do my first derivative on the left side of my page. Quotient rule says take the derivative of the top times the bottom. So the derivative of negative 12 is just 0 times the bottom, which is x plus 3 to the power of 3. Minus the top, which is negative 12, times by the derivative of the bottom. Well, the derivative of the bottom here, like I said before, is going to be a chain rule piece. The 3 is going to have to come down, so it'll be 3 times x plus 3 squared times by the derivative of the stuff on the inside. This is where I say it's not actually all that interesting, because if you look at the inside of this function, the derivative of x plus 3, well, the derivative of x is just 1, the derivative of the 3 is 0, so this is just times by 1, which is the derivative of our x in there, right? So not super interesting, but still, you can't miss the chain rule. It's important, right? Anyway, this is all going to be divided by. This is the weird part of quotient rule. I find people often forget this last step. It's all divided by the original denominator, squared. So it'll be x plus 3 cubed all squared. Let's clean this up because this looks like an absolute nightmare right now. 0 times x plus 3 to the power of 3 is just nothing at all, so that's just gone. This double negative is going to make it positive. It's also going to combine with the 3 there, like that 12 times 3 is going to happen. The times by 1's not doing a darn thing. So what this cleans up to is the first derivative equals negative 12 times 3 and then made negative again. Well, that's going to be positive 36 times x plus 3 to the power of 2. And then on the bottom, x plus 3 to the power of 3 to the power of 2. That's a power of a power. You just multiply the exponents. So that'd be x plus 3 to the power of 6. There is one more thing we can do on this, though. Notice we have x plus 3 squared on the top and x plus 3 to the power of 6 on the bottom. Those can kind of cancel. That's just going to drop this down to an x plus 3 to the power of 4. So long story short, we have our first derivative equals 36 over x plus 3 to the power of 4. Now, here is what we're going to use to find our second derivative. The second derivative can be found just by repeating that step all over again. I'll even just switch to a different color so you can see it stand out. So we'll do the second derivative over here. Once again, this is going to be a chain rule question. So let's take the derivative of the top, which is just going to be 0, times by the bottom, which is x plus 3 to the power of 4, minus the original top, which is 36, times by the derivative of the bottom. Well, that time it's going to be 4 times x plus 3 to the power of 3. And then once again, don't forget your chain rule piece, multiply by the derivative of the inside of it. Once again, though, the derivative of x plus 3 is just 1. So no big surprise there. As for the denominator, it's just your original denominator squared. So it'll be x plus 3 to the power of 4 all squared. Let's start cleaning this up. So the second derivative equals, well, keep in mind, 0 times this is just gone. Negative 36 times 4, that's a little bit tough, but it's going to be negative 144. So negative 144 times x plus 3 to the power of 3 over, well, x plus 3 to the power of 4 to the power of 2 is x plus 3 to the power of 8, because remember, when you take a power of a power, you multiply your exponents. And then just like before, notice we have x plus 3 on the top and x plus 3 on the bottom. They're actually going to partially cancel each other out, right? So 3 on the top are gone, 3 on the bottom are gone. That's going to drop that down to a 5 on the bottom. Long story short, your second derivative, that's a horrible looking F. Hold on, let me fix that. There we go, hold on. The second derivative, f double prime of x, is going to equal negative 144 over x plus 3 to the power of 5. Awesome, right? Whew, okay, so that was quite a lot. That's it for review for today. I am also going to go over some natural log stuff. We're just going to fly through this. It's all stuff that you would have seen before, but hopefully at least like this review stuff does help. It helps you identify when you have a quotient rule, product rule, chain rule, all that jazz, right? Anyway, here we go. So first of all, recall natural logarithm. Last class, we introduced the natural logarithm, which is ln of x, right? I usually write it like that, ln of x. This works the same as regular logarithms. It just has a base of e, which is an irrational number called Euler's number, which is approximately equal to 2.71828, blah, 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 right? It goes on forever and ever. Just remember that a logarithm, like if we did some logarithm like log base b of x equals y, they're interchangeable with an exponential function. An exponential function is just something where we have a variable up in the exponent, right? The base of the log, so whatever number's down there becomes the base of our exponent. The answer to the log becomes the exponent itself, so b to the power y, and the stuff inside the log becomes the answer to the exponential. So it's kind of a big switcheroo, right? Now, a natural logarithm is just where e, Euler's number, is the base. So it's like log base e of something equals y, right? Interchangeably, this just means e to the power of y equals x, or whatever, right? So instead of writing log base e, mathematicians just came up with ln, right? That means the exact same thing, okay? Anyway, moving on. So what is E? Well, E represents the maximum possible result after continuously compounding a 100% growth over one time period. It's quite a lot. That's like a lot to bite off all at once. Basically, it's just like your ideal growth rate, right? So last class, we noted that for n number compounding periods, E would be equal to the limit as n approaches as n approaches infinity of 1 plus 1 over n to the power of n. Now, for many real-world scenarios, this isn't realistic, but for continuous scenarios, such as gradual temperature change, growing biological organisms, etc., it can find some use. Hold on, excuse me. There we go. So E equals e to the power t, where x equals e to the power t, where x is the amount of growth and t is the amount of time passed with 100% continuous compounding. We don't really need to get into this yet. It's going to be more important, especially when we get into our applications of derivatives questions. What we do need to know, though, is how to find the derivative of a natural log, because that's kind of the point of this unit. We're just finding derivatives, right? So if we had a natural log, like let's say our function was the natural log of x, then the derivative of that function, in other words, the slope of the tangent for that function, would equal 1 over x. You don't need to know why this works. It can be proved using the definition derivative along with a bunch of logarithm laws, but it is a tough one to prove. So we just need to accept this for now. Like if you're really interested, you could look it up, but it's not really worth our time. This derivative, by the way, I'm pretty certain it is on your formula sheet as well. So it's not something you have to memorize, but it is something you'll want to be familiar with. All right, anyway, let's do some examples. I'll walk you through these ones. It won't be like the beginning of today where we paused it or whatever. Let's look at this first example. Find the derivative of f of x equals ln x to the power of 4. So if this was just straight up f of x equals ln x, you'd say, oh, the derivative is 1 over x, we'd be done. But there's more going on inside this logarithm than just an x. It's an x to the power of 4. And because of that, we have to assume this is a chain rule question. So not only are we going to take the derivative of the ln on the outside here, we also have to take care of the fact that we have x to the power of 4 on the inside of the function. So here's how it's going to look, right? So the derivative of f, let's take the derivative of the outside of this function. The stuff happening on the outside out here is just ln x to the power of 4. Well, the derivative of ln is 1 over the stuff inside of it. So it would be 1 over x to the power of 4. Notice the ln had x to the power 4 inside of it. So just like it was usually 1 over x, it's actually 1 over x to the power 4. But then your chain rule comes in. So then we have to times this by the derivative of the inside of the function. Well, the derivative of x to the power of 4 is 4x3. So if I were to rewrite this a little nicer, I'd write this as 4x3 over x to the power of 4, because the 4x3 is just going to multiply by the 1 on the top. But hopefully what you see is there's stuff on the top and the bottom that'll actually cancel. So in a very weird sense, actually, because x to the power 3 will cancel out 3 of the x's on the bottom, this is actually just going to give us 4 over x as our derivative for that function. So it is important to understand that the derivative of ln is 1 over whatever was inside the ln, but you also have to remember to take the derivative of the inside of the function as well. Anyway, let's see another one. So find the second derivative. Oh, that's interesting. Second derivative of f of x equals ln 3x5. I think this one's pretty crystal clear. We've got some chain rule piece inside here for sure, right? Let's start by taking the first derivative. So the first derivative of this is just going to be the derivative of the outside of the function, so just the ln stuff. Well, the derivative of ln is 1 over whatever was in there, so it'll be 1 over 3x to the power of 5. But then we have to times by the derivative of the stuff on the inside. Well, the derivative of 3x to the power of 5 would be 15x to the power of 4. So if I rewrite this, this is now 15x to the power of 4 over 3 times x to the power of 5. Now, there's a fair bit of cleaning up that can happen here. Obviously, the x to the power of 4 and the x to the power of 5, they're going to partially cancel each other out. But then we also have 15 divided by 3. Well, 15 divided by 3 is just 5. So that 5 is just going to be left over on the top. So we can say our first derivative is just going to be 5 over x, right? Now we have to take the derivative of this function. So the derivative of this function, the second derivative, in other words, is going to be a little trickier. This is the derivative of 5 over x. There's no ln here anymore, so we can't just use that ln derivative or whatever. And this derivative might look a little bit sketchy to you. You got a couple options. You can either use the quotient rule on this, so that's where you take the derivative of the top times the bottom minus the top times the derivative of the bottom. Whatever floats your boat, go for it. Myself personally, though, I think it'd be easier for me to imagine 5 over x, like this first derivative, as just being 5 times x to the power of -1. Remember, negative exponents are not our friend at all. We don't like using them, but they are useful if you're taking a derivative. We just don't like looking at them in our answer. So if I imagine 5 over x as being 5 times x to the power -1, taking the derivative of this just involves using the power rule. The -1 is going to drop down out in front, so that's going to make it -5 times x, and then the exponent has to drop down by 1, so it'll be x to the -2. Now, again, like I said just a second ago, we don't like negative exponents. They're not our friends. So what we do is we change that back to a positive exponent. To change a negative exponent to a positive exponent, you just put it in a denominator. That's about it, right? So this will be -5 over x to the power of +2. And that would be our second derivative. All right, so we're almost done here. I think we've only got one last question. Here we go. So find the derivative of f of x equals sine of 5x squared plus 4 times ln 8x squared. Holy smokes, there's a lot going on here. Let me break this down for you. We got to actually understand what's all going on. I think one thing that's pretty clear off the bat, oops, I didn't mean to hit there. One thing that's pretty clear off the bat is that we have a product rule piece. So we got this times this. So product rule is kind of the big thing going on here. But we also, given that we have a function inside of the sine and we have a function inside of our ln, we got a couple chain rule pieces going on here as well. So the overarching look of this is a product rule because it's something times something. But when we take the derivative of each piece of that product rule, we're going to have to do the chain rule on it as well. I'm going to tell you right now, this is not going to clean up very well. You got a lot of space here, though, in your booklet. I think we'll be able to clean it up just like once sort of thing. But either way, let's just get this started. So the derivative of this, f prime x, if we're doing the product rule on this thing overall, we'll have to take the derivative of the first thing first. So the derivative of sine 5x squared plus 4, well, that'll be cosine 5x squared plus 4. But then we have to times that by the derivative of the inside of that function, because that's our chain rule piece, right? So we have to also times by the derivative of 5x squared plus 4, which is actually just 10x, right? Because the derivative of a 4 is just nothing. So that's our first piece. Now we have to times by the second piece. The second piece is just ln 8x, or sorry, ln 8x squared. So ln 8x squared, nothing we have to do with that. That's just the second piece. Plus, because product rule says you got to add these together, plus the original piece, which is just sine 5x squared plus 4, times by the derivative of the second piece. Well, the derivative of the second piece is going to be a bit brutal. This is going to be 1 over 8x squared, because that's like the derivative of our ln piece, right? So 1 over 8x squared. But because there was something inside the ln, we also have to multiply that by the derivative of that thing inside the ln. So the derivative of 8x squared, which I'm pretty sure would be just 16x. And that's about it, right? So there's our first part of our product rule plus our second part of our product rule. There isn't a lot that can be cleaned up. Like if you look at this whole left part of it here, none of that is going to be able to be clumped together, nothing at all. But one thing that could be cleaned up is this section right here. I know for a fact that if I put this as 16x over 8x squared, the 16 and the 8 will cancel out partially, and the x squared will cancel out partially. So if I just even write this right here before I do a whole new step, this is 16x over 8x squared. Well, the x's cancel out, so that drops that down to a 1x on the bottom. And 16 divided by 8 is just 2. So that's just 2 over x is what we have in this whole chunk right here. So if I'm going to rewrite this whole thing, honestly, you could have skipped this step. It's not really that much cleaner, but I don't know. I just feel like I should always do it. The first derivative equals, we could say it's cosine 5x squared plus 4 times 10x, all times by ln 8x squared, plus sine 5x squared plus 4. No big surprise there. Everything's all like copied and pasted down. But then this is now times, instead of this big chunk, it's just times 2 over x. And as much as that's a little bit cleaner, honestly, it doesn't really help too much. But if you can clean anything up, it's always a good idea to do so, just wherever possible, right? Anyway, I think we're done. There it is. So for practice, lesson 4, derivatives of natural logarithms worksheet. That was the one from last class. That, again, is in your worksheet booklet. And any previous worksheets that you still need to get done, I would really, really highly advise getting through those as well. A really good strategy right now, by the way, would be to work with a partner and make sure we understand some of these early early derivative rules, especially that stuff at the beginning of today's lesson. If that was tough for you, you might want to review that as well. Anyway, if you need any help, please reach out. Best of luck.